Welcome in Dark Core. Astronomers studying a rare Einstein cross found something they never expected, a fifth image that shouldn't exist. It turned out to be the mark of a hidden dark matter halo, giving us a new way to study the invisible mass shaping our universe. In this video, we'll break down how this discovery was made and why it matters. The story centers on her S3, a dusty, star-forming galaxy more than 11 billion light-years away. Normally, galaxies at such distances are faint and difficult to study, but in this case, its light passed directly behind a group of foreground galaxies whose combined gravity acted as a lens, magnifying and splitting the image we see from Earth. This arrangement produced a phenomenon known as an Einstein cross, where a single galaxy appears as 4 points of light arranged symmetrically around the lensing object. These systems are rare but well understood, and they serve as powerful tools for studying both the background and the foreground galaxies. When astronomer Pierre Cox examined data from the NOM radio telescope array in France, he saw what looked like a typical Einstein cross. But in addition to the 4 expected images, there was a bright point in the center. The team initially assumed a technical issue. Instrumental glitches are not uncommon in complex arrays. But after reprocessing the data and checking the calibration, the central image remained. To verify, they used the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile. ALMA confirmed the same structure, 5 images of her S3. This was highly unusual. Einstein crosses are predicted to show 4 images, no more, no less. A central image simply doesn't occur under normal lensing models. As Rutgers astrophysicist Charles Keeton noted, you can't get a fifth image in the center unless something unusual is going on with the mass that's bending the light. Spectroscopy showed all 5 images came from the same galaxy, proving the fifth was real. The challenge was that 4 visible galaxies couldn't explain it. Only unseen mass could. To solve the puzzle, researchers built detailed computer models of the lens. They mapped the positions of the 4 visible galaxies and assigned them masses based on their luminosity. When they ran the simulations, the result was clear: the models could not reproduce the 5-image pattern. Adding more detail about the galaxy's possible shapes or positions didn't help. The physics of the visible matter simply didn't allow for a central 5th image. The only way forward was to include an additional invisible component, a dark matter halo. With the halo added, the simulations aligned with the observations. It appeared naturally positioned and magnified exactly as seen in the telescope data. This conclusion is significant because it offers direct evidence of dark matter's influence at the scale of a galaxy group. Astronomers already know that it makes up most of the universe's mass, but its distribution in smaller structures is harder to measure. This system provides a rare detailed case study. The finding also feeds into larger scientific questions: the distribution of dark matter. Does it form smooth halos or are there dense clumps and cores? The 5th image suggests that concentrations of it can strongly affect lensing patterns. It also helps test cosmological models. The standard model of cold dark matter predicts halos around galaxies and groups, but anomalies like this refine our understanding of how they form and evolve. The lensing of her S3 also aids in studying the distant universe. The gravitational lens magnifies the galaxy, allowing astronomers to study its star formation, gas flows, and structure more clearly than would otherwise be possible. Methodologically, this case highlights how gravitational lensing doesn't just magnify distant objects, it also acts as a probe of the invisible matter in the foreground. It shows that dark matter halos aren't just theory, they are measurable parts of the universe's structure. The unusual Einstein cross is more than a striking visual. It serves as a test case for probing dark matter in ways few other systems can. By analyzing the positions and brightness of the images, astronomers gain precise information about the amount and distribution of mass in the lensing group. The research team has gone further, making testable predictions. For example, they expect that future high-resolution observations will reveal features such as outflowing gas from her S3 magnified by the lens. If those predictions are confirmed, it will validate the halo model. If not, it could point to new complexities in either its distribution or the behavior of the background galaxy. This process illustrates how astronomy advances. An unexpected result challenges assumptions, and in trying to explain it, researchers refine their models of how the universe works. Future instruments will deepen this work. The James Webb Space Telescope can examine her S3 in infrared, revealing its stellar populations and dust structure. The upcoming extremely large telescope in Chile will allow even more precise spectroscopy, measuring the motion of gas and stars within the lensed galaxy. Meanwhile, wide-field surveys are expected to discover more Einstein crosses and other lensing systems. With more examples, astronomers can determine whether this fifth image anomaly is unique or part of a broader pattern. If similar cases are found, they could collectively map dark matter on scales ranging from individual galaxies to groups and clusters. The broader implication is that gravitational lensing is not only a method to study the distant universe but also a tool to investigate the invisible structures shaping it. Each new anomaly adds to the evidence that dark matter halos are central to cosmic evolution. This discovery highlights global teamwork, with NOM, ALMA, and international support turning a suspected glitch into a window on dark matter. The fifth image turned a puzzle into proof of dark matter's hidden influence. Each discovery like this brings us closer to understanding the universe's invisible framework. Want to dive deeper into cosmic mysteries? Stick around and watch our next video. Thanks for watching Dark Core.